Hello, this is Professor White. I will be discussing with you about the chemistry of life. Now, first and foremost, why are we studying chemistry? Well, chemistry is the foundations of biology. As you know, and throughout this course, you will see the connection between chemistry and biology, especially in our lessons on cells and all that. So, just a perspective, we know that in the hierarchy of life, this is basically the sequence. Atoms, elements, compounds, organelles, cells, tissues, organs, organ systems, to comprise organisms. So we will focus today on elements and compounds for this session. Now we know that everything is made of matter, and matter is made of atoms. Atoms are made of proton, which is a positively charged particle, neutrons, which is a neutrally charged or zero charged particle, and electron, which is a negatively charged particle. Now here's an example. Hydrogen has 1 proton and 1 electron, while oxygen has 8 protons, 8 neutrons, and 8 electrons. Now where can we find this? Well, obviously we know from high school or middle school that elements are arranged in the periodic table of elements, and different kinds of atoms, different elements. So as you can see here, the most common that we have are your hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfate, which is very essential to life. So here is an example: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So, having said that, we know that all of these that I've highlighted right now are pretty essential. And life requires about 25 chemical elements. And 4 elements make up 96% of living matter, such as your carbon, oxygen, hydrogen, and nitrogen. Now, 4 elements make up most of the remaining 4%, which is your phosphorus, sulfur, calcium, and potassium. Now, there are some trace elements. They are only required in very small amounts. For example, in vertebrate, they need iodine, which is required for normal activity for the thyroid gland. Now, in humans, iodine deficiency can cause goiter. So let's move on to bonding properties. So the bonding properties affects the electrons. Okay, as you know, electrons determine the chemical behavior of atoms, and it depends on the number of electrons in the atom's outermost shell, as you can see here, the red dots right here surrounding the nucleus. Now, you call this outermost layer as your valence shell, and this is where the action happens. So what is the effect of that on electrons? Well, the chemical behavior in an atom depends on the number of electrons in its valence shell. So this is basically the electrons that we count, because they're the ones responsible for bonding. So how does this atom behave? So as you know, that these are 2 different elements with different amount of outermost electrons. So the one on the left hand side has 1, 2, 3, 4, 5, 6 valence shell, the outermost layer, while this one on the right only has 2 valence electrons. So this is kind of like an organizer, so you can see the outermost valence shells of each of the most common elements. Like your hydrogen has 1 valence electrons, helium has 2, lithium 3, beryllium 4, all the way to the 3rd shell. As you can see, sodium has 1, magnesium 2, aluminum 3, and so on. So this is basically the elements and their valence electrons. Okay, so elements in the same row have the same number of valence electrons in our periodic table. So this one from left to right in your periodic table, you'll see that their valence shell is they in the same row. Okay, and moving from left to right, you know that each element has a sequential addition of electrons. Now, elements in the same column, okay, have the same valence and similar chemical properties. Okay, so you can see there, these columns that I'm highlighting right now, they have same valence and similar chemical properties. Now, atoms tend to complete a partially filled valence shell or empty a partially valence shell, just like as you can see over here. And if that happens, of course, the tendency is to drive chemical reaction and create what we call bonds. Now, all atoms of an element have the same number of protons but may have a different number of neutrons. Now, isotopes are two atomic forms of an element that differ in number of neutrons. Now, radioactive isotopes decay spontaneously, giving off particles and energy, as you can see here in this example. So this example here, a cancerous throat tissue, basically this is a PET scan, which is used for identifying that cancer and using a radioactive isotope. Now, bonds in biology. So why are bonds very important? First and foremost, there are what we call weak bonds. And these weak bonds are normally hydrogen bonds, which is an attraction between a positive and negatively charged particle. And mostly it's hydrophobic and hydrophilic interaction. Hydrophobic means water-fearing, and hydrophilic is water-loving interactions. This is an interaction that happens in water. So van der Waals interaction, that's another thing, which is another type of weak bond, as well as your ionic bond. Now, there's also strong bonds, and these are called your covalent bonds. Okay, so here's the diagram of a hydrogen bond. So it's a bond between hydrogen, that's why it's called hydrogen bonds, and covalent bonds over here with hydrogen gas. When they bond together, that's a covalent bond. So why are covalent bonds strong bonds? Well, two atoms actually share a pair of electrons, both atoms holding on to the electrons, which cause them to be very stable. It mostly form molecules right here, as you can see here in this example. You can see the hydrogen gas forms a covalent bond wherein they share electrons. So you can see here on the diagram. And the other one is, of course, your water. Okay, so as you can see here, this is your covalent bond. Now, there is such a thing as multiple covalent bonds. So if there are two atoms can share one pair of electrons, you call that double bond. Now, there are two pairs of electrons, and basically that's your double bond. Now, if it is triple bonds, there are three pairs of electrons, okay, shared. And normally these types of bonds are very, very strong bonds, which is why the more the better. Okay, so we have double bonds, triple bond. Now, there is another covalent bond called non-polar covalent bond. Now, the pairs of electrons are shared equally by two atoms. And an example here is your hydrocarbon, or just to be specific, is methane, or CH4. C is that black molecule right there, and then the H4 is the red ones. So as you can see, it's balanced and stable, and it's a very good building block. Now, polar covalent bond pair is a pair of electrons shared unequally by two atoms. So example is your water, H2O, because oxygen has a stronger attraction for the electrons than hydrogen. So that's the reason why they are unequally shared electrons. Now, oxygen has a higher electronegativity, and water is a polar molecule. So positive versus negative poles are kind of like their tug of war type of thing. Okay, and because of this unequally shared electrons, this leads to many very good properties of water, which we'll discuss later. Now, hydrogen bonding. Now, when you say hydrogen bonding, water, by the way, polar water creates molecular attractions. And attraction between a positive in one H2O molecule to a negative O in another H2O happens and creates that attraction. Now, going back to what I mentioned about the interesting properties of water, we're going to be talking about why water is such a unique compound. So as you guys know, the reason why we're studying water is because all life focuses in water. inside and outside the cell. Now, as a chemistry of water, we know that water is made from H2O molecule, which forms hydrogen bond with each other, wherein H plus is attracted to O minus and creates this sticky molecule that you know, and I'm sure you love drinking water as well. Okay, so water has special properties. One of them is cohesion and adhesion. So cohesion and adhesion has to do with the surface tension and the capillary action. I'll explain that in a bit. And the second, water is a good solvent. Many molecules can dissolve in water. Some molecules are hydrophilic versus hydrophobic. We'll talk about that in a bit. The third is your lower density as a solid, wherein ice floats. It has high specific heat and it's high heat of vaporization. It heats and cools slowly. So let's start first with cohesion. So when you say cohesion, it is a bonding between, it's a hydrogen bonding between two water molecules. Water is sticky, and that's why it has a good surface tension. Just like when we drink in a straw, water can stick, right? Also, another example of cohesion is that you see those droplets of water, because water tend to stay together and stick together. Now, adhesion, on the other hand, is a hydrogen bonding between water molecules and other substance. Okay, so that causes that capillary action, just like in the stem of plants. Okay, also the meniscus that you can see, as you can see from the outside of the glass and all that, and as it climbs up to be seeped into your paper towel or cloth. Okay, so this is another example of surface tension right here, and of course your adhesion. Okay, so how does water get on top of the trees? Well, transpiration is built on cohesion and adhesion. Okay, as you can see, as water climb up, so that the water gets up to different parts of your tree, that is contributed to water's unique property of cohesion and adhesion. Now, second, water is a solvent of life. Now, polarity of water makes it a good solvent. Now, polar water molecules surround positive and negative ions, and solvents dissolve solutes, creating solutions, as you can see over here. So when water, you dissolve the salt and water, it dissolves, and it is because of this polarity of water. Now, what dissolves in water? So whatever substance which is hydrophilic, or we call that water loving, the substances have attraction to water, and they are polar molecules. Polar molecules dissolve in water. Now, what doesn't dissolve in water? These are the hydrophobic substances, which don't have an attraction to water, and you call those non-polar, such as your fats or oils. Now, the third property of your water is that most substances are more dense when they are solid, but not water. So as you can see, ice floats, and basically because hydrogen bonds form a crystal, and that crystal causes that water to float. So you can see here in another diagram that hydrogen bonds are stable when they are frozen, and in liquid water, hydrogen bonds are constantly breaking apart and reform, whereas when it's ice, they are in a stable, kind of like a lattice. Why is ice floats important? Well, oceans and lakes don't freeze solid, okay, and surface ice insulates actually the water from below, and as a result, it allows life to survive in the winter because of it. And if ice sank, then ponds, lakes, and even oceans would freeze solid, and in the summer, only the upper few inches would thaw. And there's some seasonal turnover of lakes, sinking cold water cycle nutrients in the autumn time. So here's some examples of this diagram of this particular segment of why ice floats important. Okay, so the next one is your specific heat. So water resists change in temperature, and that's contributed to specific heat. So when you say specific heat, it's like the amount of heat that a substance needs to increase its temperature by 1 degree. And it takes a lot to heat up water. And also, it takes also a lot to cool it down. And which is why water moderates the temperature on Earth. And the last one is your heat of vaporization. So when you say heat of vaporization, is the amount of heat that will cause the water to change from being liquid to gas. And as you can see over here in this diagram, it takes about 100 degrees Celsius for water to start evaporating and to become water vapor. Okay, so that's ice, so B and C, ice and liquid water melting. And then this part right here from D to E, this is your liquid water to becoming vapor. So just to summarize this property of water, organisms rely on heat of vaporization to remove body from heat, which we call evaporative cooling. Now, the next one is ionization and water and pH. Now, water ionizes, which means hydrogen ion splits off from water, leaving OH minus or hydroxide ion. Now, if H plus is equal to the OH minus, water is neutral. If the H plus or hydrogen ion is greater than the OH minus or hydroxide ions, then the water is acidic. And if the H plus is less than OH minus, then water is basic, which of course contributes to our concept of pH. Now the pH scale of how acidic or basic solution is from 1 through 7 to 14. Okay, so as you can see here, this is the equation of like how much hydrogen versus hydroxide to see if the substance is acidic or basic. Now in this pH scale, as you can see here from top to bottom, top having the most amount of acidity, and down below is your most basic. Hydrochloric acid is 1 all the way down to sodium hydroxide, which is 14. Now pure water is 7, which is a neutral pH. Now buffers. So what's the importance of a buffer? Now the pH of cells must be kept at 7, and the pH affects the shape of molecules, and therefore the shape of molecules affects its function, and therefore pH affects cellular function, and therefore there's what we call some buffers that controls the pH changes in the cells. And there is what we call these reservoirs of H plus that kind of like balances it off when a certain environment in our body becomes acidic. And so what it does, it donates hydrogen when hydrogen falls, or absorbs hydrogen when hydrogen plus or ion rises. And that's about it for this chemistry of life review that you guys need to know about. I will have another part of the video for our macromolecules after this. I'll see you in class. Bye.